Everybody, coming to you with another fun problem from the Singapore Mathematical Olympiads SMO. That's the junior section back in 2007. Now this is a strange problem. I almost gave up on this thing, but it says find the value of A such that the two equations, these are two quadratic expressions here, have one common real root. One common real root. All right, so we want to avoid complex solutions here. Now, before I dive into this thing, I want to just point out something that comes in quite handy later on here. Let me get the marker working here. Okay, something that's very useful in terms of relating these coefficients to the zeros themselves is just to think about the factorization. We'll just use the same letters I chose here. We'll use the subscripted variables. Let's say x sub 1 and x sub 2 are zeros of this expression here. Okay, so that means you can, according to the factor theorem, you can write it like this. There's a couple of factors juxtaposed here. Okay, now when you expand this out, you end up getting x squared, of course, and then just by the distributive property, you're going to end up, they call it foiling, I guess, sometimes, but don't like that term so much. So you have x sub 1 plus x sub 2 all times x, and then plus the product of the zeros, which would be x sub 1, x sub 2. Sorry about that. Yeah, that's x sub 1, x sub 2, folks. But what's more important here is the fact that the coefficient of x is minus the sum of the zeros. The coefficient of x right here is minus the sum of the zeros. Okay, now that will come into play here. Now, what I did is it said you do have a common real root, and so I'll let x sub 2 be the common real root, and I just rewrote the equations. Okay, the left-hand side, or this piece right here, is just substituting x sub 1. I call the zeros x sub 1 and x sub 2 for the first equation. All right, and here's the statements of that. And then for the second equation would have a zero in common with the first equation. I wrote x sub 2 again right here. Okay, so you can see that x sub 2 appears twice to take care of this condition right here. All right, now it turns out this side wasn't so important. All I had to do, at least, was just subtract these two equations from each other. Or term by term, I just subtracted this bottom equation from the top equation. Now notice when you subtract x sub 1 squared minus x sub 2 squared, that is the difference of two squares, and I went ahead and just wrote that down. Or this object right here, x sub 1 squared minus x sub 2 squared, is given by this formula right here, very well-known formula. Okay, and then of course I subtracted. When you subtract off the x sub 2, it becomes a plus x sub 2 right here. Ax1 minus x sub 2 is exactly what you see right here. And of course, 1 minus a negative a is 1 plus a. Now here's where this piece right here comes handy. The sum of these zeros right here, this would just be minus a right here, right? Okay, that would be minus a, which is what I replaced it with. Okay, or if a is the sum of the zeros, x sub 1 plus x sub 2 is the sum of the zeros, the minus sign hangs here. And so you have x sub 1 plus x sub 2 is minus a. Tremendously simplifying situation. I mean, it really helped things quite a bit. What you can see right here happen is that this minus ax1 is going to cancel with this plus ax1, right? Okay, so you see that went away, and then you have ax2 plus ax2, so you just factor that out, and you get this much simpler expression right here. All right, and so now at this stage, this is just factoring. A plus 1 is common to both of these terms, and so we end up with this factored binomial here. Now, one of the solutions here that I didn't write down is one of the solutions would be a equals -1 here. And you probably can see why I didn't write it down. A equals -1 is certainly a solution to this. And then, of course, x of 2 is equal to -1 is the other solution. But look what happens if you use a equals -1 right here. If you pop a equals -1 right here, you would have x squared minus x plus 1 equals 0. But notice here that that'll be a problem because notice you will have complex solutions here. The discriminant here would be, I'll just write out the square root 2. Would be -1 minus 4 would be -√3, okay? I'll just write down the result there. See, so we would have a negative discriminant here, which would be complex solutions, right? It would be imaginary solutions, would be non-real solutions if you did the quadratic on this or you completed the square. B squared minus 4ac would give you minus 1 squared is 1, minus 4 is -3, right? So we have to reject this. We can't, we can't use that because we're looking for real roots, right? Now the other one works out just fine. X of 2 equals to -1. You can see very quickly that if you put that works out fine, that implies that a would have to equal to 2. You can check it in either spot right here. Like if you want to check it right here, if x of 2 is equal to -1, right here you would get 1 plus 1, it's 2, equals to a. All right, and very same thing over here. You can verify. All right, but in any event, a is equal to 2. That's the answer to the question. Let me know what you think. I may have done it put in a little bit too much work, but a equals 2 is the solution to this problem. A equals 2 guarantees you'll have a common real root, and we even know what it is. X of 2 would be equal to -1. The solution a equals -1 would lead to complex solutions, and that would rule out the possibility of a common real root.